The rules are you can ask a question anytime, and you should understand that if you don't understand, it's likely that other people around you don't understand, and it's likely that I didn't explain well enough, so you should say something, okay? What I'm going to do is I'm going to go through dynamics, at least applied theory and dynamics, essentially from the beginning of where it started until the end of what you saw yesterday if you were in the course yesterday, okay? So if you go back to the sort of 1990s when we started doing all this, we were developing models to empirically analyze questions in I/O. And the way we did this is we took the frameworks from theory and we tried to incorporate the richness of markets like demand systems, contractual relationships in the market, et cetera, okay? So the idea from theory basically was just Nash equilibrium of various forms, okay? So everybody's doing the best they can given what everybody else is doing. And from econometrics, we took methodology for incorporating both observed and unobserved heterogeneity into these models, okay? So, and it started essentially with take it or leave it offers in a full information game. Take it or leave it, like retail trade. There's a price out there. You either take the price or you leave. Okay, you don't bargain with the guy. Okay. It's been extended a lot. I'm not going to go there, but to allow for asymmetric information, bargaining models, non-price allocation mechanisms like kidney exchanges. So it's been, and schooling systems. I'm not going to go there, but there's been a lot of that, okay? I'm going to go straight to the dynamics. And we started exactly the same way we started in the static models. That is, we started by taking the frameworks from the theory colleagues and then made assumptions which were more rich, which allowed for heterogeneity in various kinds of issues. The two basic assumptions that we took from the theory colleagues were state variables evolve as a Markov process, okay? And the equilibrium is some form of Markov perfection. Everybody, again, is doing the best they can, conditional on what they know, and what they know is last period's values of the state variables, okay? So this starts way back in OR with Star and Ho, but the most direct thing to I/O starts with Baskin-Tirole, 3 articles, and 2 of them in Econometrica and 1 in the European Review. And when we started trying to adapt the dynamic framework to the richness of real-world institutions, just like we did with static stuff, okay? So the framework for doing this is usually this paper I wrote with Rick Erickson. This started when I was still a student, okay? Rick was a first-year graduate student, a first-year assistant professor. So I'm going to go through that and then show you where we got to today. So let's just take a model where every firm has one state variable, okay? And it lives on the integers, on the positive integers. So then let SI be the number of firms with efficiency level I, okay? So then a market structure, just a vector of these SIs. How many firms have market, efficiency level I? How many firms have efficiency level I plus 1 and so on? That's a vector. Okay? And that's what we call an industry structure, okay? And then in addition to that, there's an aggregate state variable that evolves exogenously, usually as a Markov process. So it's, essentially in a demand system, it would be the outside alternative. So you're playing against things that are in your market, but also there's stuff outside of your market that people could go to instead of staying in your market. Okay, so the model is set up with something like this. My value, I'm I. When the industry structure is S, I can either exit and get fee for my exit costs, or I can stay in, I get current profits, which are taken from the static games that we already knew how to do, okay? Plus beta times the continuation value, okay? Where the continuation value is what my value will be tomorrow, which depends on my I tomorrow and this industry structure tomorrow. And then there's a probability distribution over the couples, my I tomorrow and the industry structure tomorrow, okay? So the simplest model is what we call a capital accumulation game, where I can write the this probability, I should use this thing. I can write this probability as a product of the probability of where I will be tomorrow, given where I am today and how much I invested, okay? And the outside alternative, and then a probability where S minus EI is just the industry structure minus 1 for where I was. So it's a distribution of your competitors, okay? And that depends on I, X, S, and C, okay? So that's why it's a capital accumulation gain. The increment of my own state, or the decrement of my own state, only depends on my own investment. Okay, it doesn't depend on what everybody else does. So, you can extend this. So for an auctions, this would be a bad thing to do. Okay, so you set a price, okay, and if it's a dynamic auction, what's going to go on, like an oil lease auction or a timber auction, what's going to go on is my stock is the amount of timber I have in stock, okay? I'm going to bid in on the next lot, okay? And whether I win or not depends not only on my bid, okay, which would be X in this case, okay, but also the bids of my competitors. That's easy to add, okay? So I'm going to keep to the simplest models, okay? That's been done, and it's easy to add. So the Q is the equilibrium object, because it's my perception of where my competitors will be, okay? So that has to be somehow consistent with what my competitors do, okay? So that's the equilibrium object, okay? This is typically thought of as being stochastically increasing in investment, and there should be an I here, and in last periods, I, okay? So that's why you invest. And this Q also embodies the incumbent's belief about entry and exit, okay? It has to do that, okay? There's many possible entry models, and the reason there's so many possible entry models is nobody knows what the right model for entry is. So, we just, because entry, you don't know where it's coming from usually. So we just assume there's, you can do any one of many things. What I'm going to do here is just an entrant must pay XE has to be greater than beta times phi. If it wasn't greater than beta times phi, you'd enter just to exit next period and get beta times phi minus XE, okay? So that's what's called chattering in the OR literature. So then you enter one period later at omega E, and you only enter if the expected discounted value of future net cash flows from entering is greater than the cost of entry, okay? So what's a dynamic equilibrium? This is a standard Markov perfect model, only it's just, I've made it rich enough so you can take in more of the institutional detail. So the dynamic, every agent chooses an optimal policy given its perceptions on likely future industry structure. So everybody's going to do the best it can, okay? And those perceptions are consistent with the behavior of agents' competitors everywhere, at every point, regardless of whether I've ever been there or not. I know what will happen at those points, okay? So that's the notion of Markov perfect, okay? So Laurits-Seltzkin's how do I prove existence? For this, you need random entry and exit costs. Most of the time, I don't use it. It just complicates things, and it always converges. The original Erickson Pakes paper proved that gave conditions where there are never more than n bar firms active, and we only observe firms on a finite set of states, okay, 1 to k. You can think of this as, it's easy to get this. If profits are bounded, then n is going to be always less than some upper limit of n. And the lowest possible state is a state where a monopolist would stay in, okay? And they showed, so why was that sort of interesting? It wasn't terribly interesting, but it did say that it's computable. It's a finite number of points. And then they proved that so in my notation, S super T will be the history of all the S's, okay? So S1, S2, S3 up to ST, okay? And S sub T will be current one. And they gave conditions where this is a Markov process, so it only depends on ST, last period. And the transition kernel which is QS prime given ST, is homogeneous over time. I'll come back to these conditions in a second. Okay. The other condition, I'm going through the conditions because I'm going to need them later, okay? They're very simple. the other condition is that they gave conditions where Q is ergodic. What does ergodic mean? I don't have a blackboard. But there's a bunch, consider a two-dimensional state space, okay, which will never be true in applied work, but just think about it for a second. So there's a bunch of points, okay? And what this says is you may not start in one of the, so there's going to be a subset of the points, which are called the recurrent class. You may not start there, but you will eventually enter the recurrent class and stay there with probability 1 forever. Is that clear? Okay. Why does that happen? It happens because your demand system and your cost system and all the primitives of the problem say only certain things, okay, are consistent with the economics of the problem. You know, it could be that I didn't start at one of those, but if I had, you know, a car which was large and had very many miles per gallon, it's just too costly to produce such a car, or the knowledge doesn't allow us to produce such a car, so we'll never see it. Is that clear? Or if the market, as you compare a small market to a large market, it's not that, you know, in a small market, I'd say population and income, okay? So in the small market, there'll be a recurrent class, okay? And when we get to the large market, the recurrent class won't include much of the small market. Why? Because eventually there'll be an entry in this larger market. Is that clear? And it may be true that I started at the small market and the city grew. Is that clear? But once it's a large market, I'll never go back. If I might do lousy relative to the outside alternative, okay? But and I might drop out. But if I drop out, somebody else will enter. It's just the logic of the profitability thing determines what that recurrent class is. Is that clear? That's important, okay? Okay, so why is that interesting? The cardinality, the amount of points in the recurrent class is less than the number of points in the states, in the total state variable. Is that clear? So if I can tell you how to compute just on the recurrent class, I have an easier computational problem. Okay? And there's limiting probabilities on this recurrent class. If I get into this recurrent class, I'm going to cycle around it. It's not a point. It's a set of points. Okay? I'm going to cycle around it. And eventually, there'll be what's called an invariant measure over this recurrent class. There'll be a probability distribution that will emerge. Okay? Sometimes that's called the steady state of the system, which is a misnomer, because it's not a steady state. Things are moving all the time. Is that clear? It's not the same industry structure. The industry structure moves all the time. It's just that it stays within this recurrent class. Okay, good. Okay, you're going to see there are a lot of computational papers that use this sort of Ericsson Pakes stuff. And you know, it was good because the things, so how did theory apply these problems? They made enough assumptions so you could get analytic results. Is that clear? And that required a lot of assumptions, okay? And there were things you just couldn't do, you know, you couldn't do analytically, okay? So a bunch of computation people like Ken Judd, Uli Dorotzelski, you know, I've written papers like this to use the framework to see what would happen if there's learning by doing, you allowed learning by doing, or you allowed collusion, you know, any, you know, new, more complicated frameworks, okay? And mostly this was done computationally. There was very little empirical work. It's sort of interesting, you know, it took me until now to do empirical work on dynamics, even though the framework is something that, you know, I worked out with Rick Erickson, because I sort of didn't believe it. It wasn't rich enough. You couldn't do what I thought you needed to be able to do to make sense out of data, okay? Doesn't mean, I mean, you shouldn't get me wrong. You should start, it's always the same in IO, at least, I think in economics. You know, you do what you can do, and the only real question, okay, is can you do better than the alternative, okay? Somebody's going to make decisions on the economy or at a firm or whatever, okay? And the only question is, can you do better than them, okay? And the answer is sometimes you can, even with this very limited set of tools, okay? And sometimes you can't. The story on cars, by the way, is when we did BLP and micro BLP, we went to General Motors. There was a guy there who had a PhD in economics from Chicago named Mustafa Muhatara. He actually became a vice president of GM eventually. But after he saw BLP, that's how we got the micro data. He saw the BLP stuff, asked us to come, we gave the paper. He said, what would happen if you had real data? That was his comment, exactly that. And so he gave us the microdata that they had, but he only gave it to us for 10 years earlier, so there was no problem with. So that's how microBLT got started. But he once asked me once, what would, could we do dynamics? What kind of car should we produce and stuff like that? And at the time, I told him my reaction was, you know more about how to do this than we do. Because he did. I mean, he knew a ton about the industry. He knew where there was missing cars and stuff like that. The SUV was the big thing that was on his mind at the time. We just didn't have the framework to do that in a realistic way. So, so sometimes we don't do that. Okay. So what do you have to do to compute an equilibrium? There's a number of papers on different ways of doing this, but it's essentially all an iterative algorithm, just like in single agent. So you have something in memory at each point. You bring it down and you update it, okay? And then you put it back in memory and you go through a whole iteration like that. So you have something in memory, which is your continuation value and profits at each point. Okay, they could be wrong. You shouldn't get me wrong, but you have something in memory at each point. Okay, you do the optimal thing given the continuation value. So you go back to this VIS, and you find the max with respect to x, and and then you see whether it's greater than what you get for exiting. If it's greater than what you get for exiting, you don't exit, and you choose the optimal x. Okay, that's it. And then you put it back into the computer algorithm, and you keep on doing it till you get to a fixed point. Okay, so what's a fixed point? At every IS, okay, V of iteration K IS equals V of iteration K minus 1 IS, or else the policies are the same. Okay. Okay, so what's the burden of this, of computing this? It's the number of points you evaluate at each. There are 3 components to it. There's a number of points you evaluate at each iteration. I'll come back to this. So I have to bring up each point, okay, and update, okay? So there's a number of points, okay? The computational burden per point, how much do I have to do to the point? And then the number of iterations, okay? So it's sort of simple. So you know the number of points is less than k to the m bar, where m bar is the maximum number of firms ever active, okay? But that can be a large number, okay? In the sort of simplest game, the burden per point is twofold. One, I have to integrate out over where everybody else will be tomorrow. Is that clear? So that also increases in the number of points that I can go to, that each guy can go to. So each guy is at an I now, and it can go somewhere else. And every combination of those things has to be integrated out, okay? And then the cost of obtaining optimal policies given the continuation value. And you can write that down as analytic expressions often, okay? So that's not the problem. So this grows exponentially in the number of firms. You can get it down to geometric if you assume exchangeability. So most of these models, I can permute. If you write it down as not S, you write down the whole S thing, okay? But you write down my I, and then the S's of everybody else. You can permute the firms, okay? It doesn't matter the order they enter, okay? So that decreases it to geometric. But if I had, only 20 points per firm and 4 firms, it's 20 to the 4. If it's 20 firms, it's 20 to the 20. Quickly, you're going to get killed, okay? And then for the burden per point, the cost of calculating expected value, if there's a positive probability on k points for each of the m minus 1 active firms, then there's kappa to the m. It also grows like that. That's the integral to get continuation values. Okay. So that's the curse of dimensionality. Those 2 things are what you hear in the literature, the curse of dimensionality. The dimension of the state space, okay, is 1, and then the dimension of the integral that I have to calculate for continuation value. Okay. So I mean, this has been used mostly for the theoretical issues, applied work before. Sometimes, like yesterday when Victor was doing stuff, Victor's problem was he used the whole dynamic framework, but he didn't have to compute it. All he did, he used a non-parametric way to correct for a selection problem. Is that clear? The same thing happened in all the Pakes. I don't know if you know that the production function paper. It's exactly the same. So I use the framework to correct for something, but I don't actually compute the equilibrium. Okay, so that's what Victor was doing yesterday. Okay, so the difficult. I mean, let me give you a simple example of how complicated this is. Think about a durable good like cars. Okay, what Mustafa asked me about cars. So what's going to go on? Each consumer has a perception of the future of cars. Okay, so he has a car that he's holding. Okay, and the question is, what am I going to do? Okay, so I'll make a choice today. Okay, there's 130 million households in the United States now, I think, something like that. Okay, if every one of these guys does this choice, okay, and then there's a profit function and continuation value if those choices are correct. Okay, for each firm. Is that clear? Each firm then chooses a price for the cars and what products it's actually going to produce. Is that clear? That won't be consistent with what the people actually thought was going to be. So they have to compute the fixed point here, and then the fixed point for each individual of 100 million individuals. Bring it back here, and then compute a fixed point for General Motors and Honda. Okay. So the problem, this is a problem that no computer can handle. Okay, and won't be handleable for many years. Okay, it's just not in the cards. Okay, so there were two different responses to this. Okay, there was a theory response which we ignored for a long time, and there was a computational response which we did not ignore. So, there was stuff by Ken Judd, that stuff on oblivious equilibrium by Lanier Benkard and his co-authors. So those were that was the computational part. Okay. So I'm going to not talk. I'm going to just tell you a little bit about approximation. But the truth is, there are people in this. They're teaching you that know a hell of a lot more about this than I do. Okay, because I haven't been doing it, and so they're going to teach it to you, not me. Okay, so there are just deterministic approximation techniques, like polynomials or sieves or splines that are used. There's a stochastic algorithm, which I will come back to a little bit. There's putting it into continuous time, which kills one dimension but not the other. There's oblivious equilibrium. I'm not going to go over this. Okay, they each have their own way of doing it. And there's people here who know more about it than me. So oblivious equilibrium is it's sort of a moment-based technique. I don't get everything, but I get moments. Okay, deterministic approximation is just I use some set of basis functions and do it. Stochastic algorithm I'll come back to because I need to use it afterwards. And the continuous time, there'll be a hit to one person at a given time. So when I do the continuation value, I hold everybody. The probability of it hitting two people at the same time is 0, okay, or goes to 0 if the time period is small enough. Is that clear? So what happens is the continuation value, all I have to do is see where I go, not where everybody else goes, and keep everybody else constant. Okay, and that kills the cursor dimensionality. Okay, good. So the question is, does assuming asymmetric information help? And one way you could think of doing this is, not everybody doesn't know everything. It's not full information. Okay, I only know certain things and I don't know other things. Okay, and that's the first thing you would think of, probably. Agents presumably know their own characteristics, and they know that they're correlated over time. So likely the characteristics they don't know of everybody else will also be correlated over time. Okay, so you get quickly to what the theorist, if the theorist did this in those days, they would go Bayesian Markov perfect. Okay, so it's still perfection. Okay, but now what I know is the distribution of where my competitors are going to be tomorrow. Okay. That works out to be about 10 times as hard to compute as the original stuff, because what you have to do then is formulate the distribution of what everybody else is going to do and make sure it's consistent with their actual actions. their choices. Is that clear? That works out to be a terrifically very much harder problem. Okay? So that didn't work so well. And I don't think it's actually been used in an empirical paper. I don't know of an empirical paper where it's actually been used. Okay? There is a question whether agents can learn the optimal policies. Okay? And I'll come back to that. Okay? So the alternatives from theory, so the alternative was what the theory guys did. Okay? And you know, the issue was the complexity of Markov perfection. For the empirical guys, it was, you know, we can't compute things. For the theory guys, it was, maybe this is the wrong way to approximate behavior using Markov perfect, okay? So what assumptions could we relax? We could relax assumptions that state variables evolve as a Markov process, okay? Or we could relax assumption that the equilibrium is perfect. It's Markov perfection. Okay, those are the two basic assumptions going on. Okay. So except in situations involving active experimentation, so when you're experimenting, the policies are necessarily transient. You don't keep the same policy over time. You're learning, and you're changing the policy for the same state. Okay? We're likely to stick with Markov processes. It's convenient, and it fits the data well. If you ever look at data and see how much last period's states affect this period's state, you pretty much pick it up. Okay? And realism suggests I can't keep too much in memory. And the third thing is we can bound deviations from this. Okay? So the one thing there are situations where we might not want to have the process be time homogeneous. So it might be that things are really changing over time. The underlying structure is changing over time, and I'll come back to that. Okay? So that's not Erickson-Pakes, because Erickson-Pakes doesn't have that in it. So the fact that Markov perfection becomes unwieldy, you know, it raises, the theory guys were right. It raises the question where some other notion of equilibrium will better approximate agents' behavior. And we would like to one that not only better approximates agents' behavior, but that we can use. You know, I mean, so, okay, so how demanding is, I gave you the durable goods example. So the theory literature, there's at least three, and there's probably more. My reading of this is not, you know, I'm not a theorist by any stretch of the imagination. But there were at least three things. They all gave up on perfection, okay? Everybody knew once, you know, if you put in perfection and you have enough states, you just can't do much, okay? So the first one was the Fudenberg and Levine self-confirming equilibrium. What happens there is you're correct on path, but you're not correct if you deviate. So, okay, if you're x, okay, if you keep on the optimal x, you're going to have the correct perceptions. Is that clear? But if you deviate, you're not. Okay? Rubinstein and Osborne and Rubinstein, I guess, in their case, it's very similar to what I'm going to go to. Each agent only knows its own actions, but somehow, somewhere, and we're not going to tell you how, okay, those actions are consistent with what everybody else does. Okay? He doesn't tell you how to get there. He doesn't tell you how to compute it. Nothing, but just that. Okay? And then Esponda and Puzo in this Econometric article had prior beliefs, did worry about convergence, but had prior beliefs that might not set positive probability on the truth. Okay? So that you could converge to something that isn't quite right. And they show you that you do converge to something that isn't quite right, but close in a certain dimension. Okay? So that's the theory stuff. The thing that's different about that and why you couldn't use it directly for I/O is they're all about learning about a fixed state. The question is, I'm here, I have my state, you're my competitors, you have your states. Is that clear? Those states don't change. Okay? I'm just learning about your behavior at that state. Is that clear? And for I/O, it's we're actually, the reason we're doing all of this is to look at the evolution of market structure. Okay, so that, you know, it's not that the ideas aren't right. Okay, it's that you need to do more in order to apply it to I/O. Okay. So the question then becomes, if we abandon Markov perfection, can we both better approximate agents' behavior and enlarge the number of things we can do? So I'm going to build this up for you now. And I'm going to start with strategies that are rest points to a dynamical system. What is a rest point? I'm doing the best I can given what everybody else is doing. Okay, conditional on my information set, what information I have, I'm doing the best I can given what everybody else is doing. Okay. So the strategies like that, they're going to satisfy a Nash condition, and the question is, what is the form of that condition? Okay. And then there remains a question of, so that would be the equilibrium notion. At equilibrium, at every point I reach, okay, at least in the limit, okay, I'm doing the best I can. Okay? Of course, it doesn't tell you how we got to equilibrium. Okay, I'm going to have to come back to that. It just tells you, if you're there, this is what it looks like. Okay? So this is this paper that I should have written down. Chaim Furshman is the other co-author on this paper. Okay? So what conditions should we assume? This is how we got to our answer. What should we assume for the equilibrium? We assume that at agents, when they visit a point repeatedly, and people are playing equilibrium, okay, they're eventually going to learn what's the best thing to do at that point. Is that clear? Okay. So, so the two conditions are: agents perceive they are doing the best they can, and these perceptions are at least consistent with what they observe. Okay. I should have said repeatedly observe. Okay. You know, it might be reasonable to assume more than this, and if you, and I'll come back a little bit to that, but, and then you just put it on top of this. Is that clear? So I'll show, it's easy to do that. You might think, for example, agents experiment and so know something about the class of things what they don't do, that they don't do in this recurrent class, a feasible action that could take them out of the recurrent class. You might assume that they've experimented there, okay, and learn that that's actually not worth doing, okay, or something like that. And that will be easy to put in. Okay, I'm going to show you how to formulate this mathematically now. Okay. I'm going to keep I as still firm and T as time, and JIT will contain, JIT is the firm's information set. So, you know, you can't make a decision that's based on things you don't know. Okay, so JIT is what you know, okay? And it's going to contain, in this simple thing, you could make this more general, it's going to contain public information, things that everybody knows, okay, and private information, things that only I know. And I'm going to call the public information CT and private information omega IT. So JIT equals CT and omega IT. I'm doing a very simple case, okay? And when I get to the empirical work, I'm going to do, it's the same thing. It's just there's more X's, you know, and some of them I observe and some of them I don't. I observe all of them, I'm sorry, but there's more of them, and there's more omegas, and some of them I observe and some of them I don't, okay? So an industry structure now is a set of information sets. Okay, every one of the firms that's active now has an information set, and for the theory part, okay, the agent doesn't need to know all this, but for the theory part, it's going to depend on that whole set of information. You know, what happens depends on that. Okay, I'm going to let the policies be MIT, and they're in some. I'm going to assume they're finite possible policies. And they have to be a function of JIT. I've got to choose my policy as a function of something I know. Okay. I'm going to assume the number of M is finite just for simplicity. I don't need that. And actually, in the empirical work, we don't assume that. And that it's a capital accumulation game again. So what's a capital accumulation game? The evolution of my omega depends only on my policy. It could depend on my policy choice, my competitor's policy choice, and where I am today. Okay. But I'm going to assume it only depends on my policy choice. So this rules out auctions and other things, but I'm just trying to get through basic stuff as fast as I can. So the public information is used to predict consumer behavior and common demand and cost conditions. And I'm going to assume it evolves as an exogenous Markov process. Again, that's not necessary. Okay, good. So the state of the system, this is now ST. I've now changed it. It's not the number of firms at each state. It's the information sets of these firms. Okay? And it's going to be finite. So again, this is standard Markov chain stuff, by the way. Yeah, sure, shoot. We are doing a game because I'm going to have to get my continuation value. I have to find out what everybody else does and where their capital stocks are going.
So it comes through how other J's
Sure.
impacts the evolution
Yes.
of my J.
Yeah. Okay. So that would be, that's the Q function that I put on before. Okay. Is that? Okay. Okay. Shoot. Go. Speak. I can't hear you. You've got to speak louder.
Yeah, so I was assuming that the agents will have some perception about the private information about their competitors. And I see that it's going to be baked into the public information. So you're assuming that everyone has homogeneous perception of others?
Yeah, it's a good question. The answer in what I'm going to do today is yes, but I could have made another subset of states where I know just yours and not everybody else's. And that won't change anything I'm doing now. And indeed, you know, the empirical work and the empirical stuff that I did yesterday, that was the truth, right? You didn't know, what you knew was what your competitors in the same ATC4 class did, the same subset, like statins were doing. But, you know, at least the sum of what they were doing, but not what the other molecules were doing. Next. Somebody else had a question? No.
I think I have a question
Yeah.
in that vein as well. So in order to form an update on your future J, you need to have some sort of expectation over the private information of the other agents.
Right.
When you're taking an action
You don't.
today, is that motivated by trying to learn about that private information?
Could be. Depends how you set up the model. Okay, you could put that in. Yeah. Again, there's an issue of the stationarity of the kernel. Okay, but that's just an equilibrium. How we get to I'll show you how we get to equilibrium. Okay. So our assumptions assume each agent chooses an action which maximizes its perception of the expected discounted value of future net cash flow. Okay. And for those states that are visited repeatedly, but not all states, okay, the recurrent class of states, okay, these perceptions are consistent with observed outcomes, okay? So, you know, okay, his perceptions can only be based on his information set, okay, because I have to make decisions conditional on my own information set. So there's going to be asymmetric information in this model. Okay, I don't know everybody's information, but somehow, okay, I do the right thing when I'm in the recurrent class, and I'll show you how, okay? Okay, so here's the conditions. If W is the expected discounted value of future net cash flow, okay, in order to make a decision, I have to have a perception of what the expected discounted value of future net cash flow is. Okay, that's what I'm maximizing. Okay? Then WM star has got to be better than WM at every JI. Okay, every possible state that I'm in. Okay? And in equilibrium, in the states that are in the recurrent class, WMJI has to equal the profits plus the continuation value. And what does that mean? It means if I knew the empirical distribution of J minus I given JI, I would just calculate that. I would integrate out over profits, which depend on, its profits will depend on JI and J minus I. But I would integrate out J minus I conditional on JI. There's asymmetric information. I don't know where my competitors are, okay? But there is a distribution, okay? And if I hit this point repeatedly, I can learn what that distribution is. That's just standard probability theory, okay? There's nothing, you know, it's the most standard thing in probability theory, okay? Similarly, I can get the continuation values. Where are they? I see. This probability is for the profit function. And then similarly, I was at JI many times, and I went to different J prime I. Is that clear? Next period. So I can learn from the data where I go from JI. I go to J prime I. Is that clear? Okay. Once I do that, I can get, you can show that you can learn. So this is, and you get to this condition, which is correct. The W's are correct. You're always going to be in a J prime I, which is in the recurrent class. Is that, okay? And if at each point in the recurrent class, I can choose, I can learn what all my competitors are doing, the distribution where my competitors go. Is that clear? And I can learn, so if I do that, then I can I can just average the profits I get and average the continuation values I get. Okay? So this is the fixed point. Okay? And that's how you learn. Now, these are the conditions. I did write it up. Good. These are the conditions so Chaim and I called Chaim Furshman is his name, experience-based equilibria. Okay, why is experience-based? Because you learn how to do everything from experience. Okay, it's very similar to Fudenberger-Levine. It's even more similar to Osborne and Rubinstein. Okay, but I read that later. Okay. So what was Osborne and Rubinstein? Just think, you're doing the right thing at every time. You only know your own state variables, but for some reason it's procedurally rational. What does procedurally rational mean? I'm doing the best I can given what everybody else is doing. Not how to get there or anything else, but that was all. And this is the same thing, only it's now a dynamic game. Okay, so I have to be procedurally rational at every point in the recurrent class. Okay? So Bayesian perfect will clearly satisfy these conditions, but so will other things, okay? Because Bayesian perfect has perfection everywhere, okay? And we know that Bayesian perfect equilibrium have multiplicity. So saying, they're a subset of these equilibria, they have multiplicity, okay? And I explained this yesterday, but it's worth explaining it again. The extra multiplicity comes from the fact that if you're in equilibrium, we're going to talk about getting to equilibrium in a second, okay? But if you're in equilibrium, you're going to be in the recurrent class. The optimal policy is going to keep you in the recurrent class with probability 1 forever, okay? But there's going to be policies, so if every possible policy, not only the optimal, but every feasible policy keeps you in the recurrent class, we call that an interior point, okay? But there are going to be points where the optimal policy keeps you inside. Is that clear? But there's a policy you could take which takes you outside the recurrent class. Okay? If it takes you outside of the recurrent class, okay, you don't necessarily know you don't necessarily have the correct value. You haven't learned about those. Is that clear? Okay. So the extra equilibrium that come in here are because, excuse me, because you could have different perceptions of what's outside the recurrent class, and that's going to give you different recurrent classes. Okay? If I think that, I'm a potential entrant, and I think you just can't enter here. It doesn't make any sense. And nobody enters here. We'll never learn what would happen if somebody entered. Is that clear? So those are the kind of things that are the extra multiplicity. Okay. So I'm going to actually give you 2 computational algorithms. The first is what I didn't do yesterday, the learning algorithm. Okay. So essentially, by the way, this the learning algorithm is essentially what people call reinforcement learning or Q-learning, depending on who's talking. But it's put into the game framework. So if you read like Britsakas and Sakilas, the guys at MIT who started all this stuff, okay, they're all doing single agent games, okay? And so this is just transferring it to multiple agents. It's actually pretty much exactly what they do, okay? Only putting in more firms, okay? The second one is the one that I used yesterday, and I'm going to show you how to do it, okay? Which is much easier, but only gets the equilibrium, okay? The advantage of the first one is it can be viewed as a learning algorithm, okay? So I can start somewhere, okay? And then the environment changes. I change the primitives of the problem. I change it in the computer, okay? And I ask what happens as a result of that. You won't immediately go to an equilibrium, okay? You'll actually start, you will eventually go to an equilibrium, but not immediately, and there'll be a learning process, and there'll be a transition path, okay? Okay. There's a question of whether the learning theory I'm going to give you now is the right approximation. That's a separate question, okay? I'm not going to, I don't know that's true, and actually we have a paper in AER which shows that it's slightly more, it's more complicated than this, okay, when in real data, but it's one way to look at it. So this is going to be slightly different from what you know about doing dynamic programming, okay? Because it's going to be asynchronous. That is, at each iteration, I'm only going to update 1 point. Is that clear? Synchronous algorithms, at each iteration, you update every point in this, okay? I'm only going to update 1 point. So, so the good part about this is that if you believed it, you could actually, do transition paths as well as equilibrium. If there's more than one equilibrium, the learning algorithm will pick one out. Okay, so you might, if you think it's a good approximation, it might pick out the one you want to get. But if you think it's a bad approximation, need not do that. Okay, and formally, it's going to circumvent both, at least formally, and it doesn't quite do it really in practice. But formally, it kills the curse of dimensionality. Okay. Okay, so I don't know why I have put this up. So the algorithm consists, you need two things. You need a location where I am today, because I'm going to update just 1 point at a time. So the location is where everybody is. Okay, the agent doesn't need to know where everybody is. You shouldn't get me wrong, but the computer needs to know where everybody is. Okay. Then there's going to be objects in memory. Okay, so just like in standard updating, you have stuff in memory and you pull it up. The stuff in memory is going to be the perceived values of continuation values at this point, okay, for every point. Okay? And it's going to also have the number of visits to each point, okay, because the precision, and it's going to be a stochastic algorithm, okay, and its precision will depend on how many times you hit the point. The more times you hit the point, the more good, because it's going to be this averaging process that I told you about before. The more times you hit the point, the more precise the average is. Okay? So in order to update the iterations, I need to update the location, I need to update the perceptions, and I need to update the the points. Okay? The computational burden now is going to be determined by the memory constraint, how many of those things I have to keep in memory. So, and then the compute time. So the compute time, you'll see, can be long, okay, which I think to me says that firms know more than I know, okay, probably. Okay, how am I going to update the location? I'm going to use just what's called greedy policies in the Q-learning literature. So I'm going to say, at each iteration, I'm now at an iteration, I have, n guys that are active at this iteration. Okay. For each of these guys, I have a perception of their value in memory. Is that clear? Of the expected discounted value in memory. I have that perception for every possible thing I'm going to choose, for all the possible policies. Is that clear? I can choose m equals 4, 5, 6, whatever. Okay, for each one of those, I have an expectation of the future. Okay? And what I'm going to do is choose the one that maximizes. That's called the greedy policy. Okay? And then there's going to be, it's one of these capital accumulation games now. I could make it more complicated, and we have done that. But it's a capital. So if I choose amount of investment, or M star here, okay, there's going to be a distribution of outcomes, which depend on where I am today and on how much I invest. Okay, so that's like in a capital accumulation game, that would be a probability one thing. For advertising or R&D or something, you'd think it was stochastic, right? Okay. So if I do that, okay, I take the optimal thing. I can take a draw from the distribution of I prime given I and my amount of investment. There's a distribution in the memory. I just take a draw from it. Okay, And so everybody does that, and I update everybody where everybody goes. And that's my location update. Is that clear? So there's something in memory which tells me the value of each action I can take for each guy. Each guy does the best thing he can. There's a random draw on the outcome for each guy, and I move the algorithm to where the outcomes were. Okay? That's all there is to it. So you can think that's how they learn. Okay? I mean, agent assumes. So I'm not going to generalize here. So ex post, what happens? So everybody did this. What happened? Well, I can compute what my perception of the value function is now after everybody moves. Is that clear? So the data go that way, okay? And now I look back at what I've got in memory, and I can compute what my perception of the value of where I got to is. Okay, what's the perception of my value? It's vk plus 1. I'm going to k plus 1 iteration now. Okay, it's the profit I got, and the profit I got is a function of both what I did and what my competitors did. Okay, and dk is the ck it should be. Okay, and then it's a continuation value, which I have in memory from the last iteration. Okay, that's my perception of what the future will be like. Is that clear? I started out in memory. I start out with these w's in memory, a w0. Is that clear? So at every future state, and I update them sequentially, and at every future state, when I get there, I can compute what the value would have been, okay, or what the value is for every m. Okay, I just bring up the profit function. I compute the profits I got that period. Is that clear? I bring up what in memory is my value for continuing from that point, okay? And I choose the optimal m for that thing, and that will be my continuation value, okay? Okay, so what is this? This is a random draw, okay, from an expectation over continuation values. If I was right, if I had the right policies, it'd just be a random draw, okay? So why don't I just treat it like a random draw and average? Okay, so my WK plus 1 is 1 over 8. This is just the way you compute an average, right? 1 over n, 1 over the number of times, n minus 1 over n, the other thing. So I'm going to update exactly like that. So this becomes my value function, okay? And I'm going to update. So if I'm much higher than I was in the previous period, is that clear? Then it's going to be moved up. If I'm much lower, it's going to be moved down. And the way the OR guys write it is like this. It's the same thing, just reorganize. Put something on the right-hand side that was on the left-hand side before. Okay. This is not the efficient way to update. I would never suggest to do it. And the reason it's not efficient, but it will work. It satisfies what's called the Robinson-Monroe conditions. But the reason it's not is because the later periods are much more precise than the earlier periods. So you want to weight the later periods more. Okay? Even if it's just do 1 million draws and throw out the first million, start again. Okay? That would help you a lot. Okay? And there are other ways of doing it. But go ahead, Pamela. I can't hear you. You've got to speak on. They're not the right thing, right? It's a random draw. It's just like, you want the continuation value, you want the average, right? And you're going to get one random draw, and that's the relationship. It's just a stochastic, so this all dates back to a really beautiful article by Robinson and Monroe. I tried to learn all this stochastic algorithm stuff. I was at Yale, I went to the library, this is a true story. I looked for books on stochastic algorithms. Actually, after somebody came and gave this seminar, and I didn't understand it. Okay, so I went, and the books were just totally complex. And then I asked David Pollard, who's a friend of mine, and he said, just read Robinson Monroe, which was a 1956 article. Okay, and it was like 6 pages or 7 pages, I can't remember. And all it says is, look, if you can't compute an integral, simulate it. Okay, and that's where all this started. And then it got more complicated. Why did it get more complicated? Because you want to do the optimal h's, and the optimal h's depend on a million things. And you can get, and then you can do it in continuous time instead of discrete time. You can make it very complicated if you want to. Okay, but it all dates back. It's just that. Okay, it's the easiest article to read that I've read in a long time. Okay, okay. So that's where this goes. Okay. Now note the first thing, that if V is the average, okay, then if I'm at equilibrium, then the expectation of V is W, which is the reason that I tend to go there. When I get to equilibrium, if I see this point many, many times, okay, I'm going to tend to stay there. Okay? You can't prove that, by the way, but at least I don't know the proof of convergence. Okay, let me just say. But it converges all the time. Okay, go ahead. Yes.
periods until the end doesn't matter.
And do you update everybody else at the same? Do you update everybody else at the same time? If you update everybody else, you're back to this algorithm. If you don't update everybody else, you've got the wrong perceptions of what everybody else is doing, in equilibrium at least.
But I use all the data, right? Do give me the equilibrium, strategy and perception, and I just forward simulate, 30
If you believe you're in equilibrium,
average. Huh?
if you believe you're in equilibrium and use everybody else's policies, you'll get an equilibrium.
So the difference between this and then forward simulating and do the average, what was the...
The question, so let me take a step back, okay? So why are we doing all this? Let me take a step back, okay? We're doing all this not because we want to explain the equilibrium in the data. We can just look at, if you believe there's an equilibrium in the data, you can look at the data and figure that out, okay? We're doing all this to be able to do out-of-sample stuff. We're doing all this to do counterfactuals. We want to know what would happen if we changed a policy, or changed a primitive, or changed something in the environment. Okay? So that's why that's not the only reason, but that's a major reason why we're doing all this. Is that clear? If you believe you're in equilibrium, okay, and you want to just find out what the current policies are, there are easier ways of doing this. Okay? It depends on the actual problem, exactly how you do it. Like, the simplest way is use first order conditions. Okay? Because they're right regardless of the equilibrium. First order conditions are necessary conditions for equilibrium, not sufficient, just necessary. You might be able to estimate all the policies from them. Maybe not. You shouldn't get me wrong. But what I'm trying to do is be able to do it for counterfactual. We want to be able to do policy. Is that clear? Or else explain history in a more detailed way than just, So let me, there have been two ways. I'll take a step back. This is philosophy more than economics, but it's useful to think about for a second. There are two ways to do empirical work. Okay, the way that a lot of the labor stuff does, okay, is they say, look, something happened in the data, okay, and I'm going to see what the result was, okay, and I'm going to do difference in difference, or I'm going to do average, whatever they call it, average treatment effects, or something like that, and I'm going to do that. Okay? That's one way of doing it. And by the way, that's a way that really policymakers really like, because you give the policymaker or the administrator, you give him one number, and that's what he wants. Okay? He wants to know a number, and okay, so that's been very successful. So I'm not trying to poo-poo it. Okay? It's been very successful. Okay? On the other hand, it's the thing that's bad about it, okay, is that if you change either the environment or the policy, it's not, so I go to a different market with a different distribution of income, or it doesn't work, it's not credible, okay? Or something else changes in the environment, it's not credible. So it is true that, in upper New York State or wherever they were doing it, and they changed something, that's what happened in upper New York State. Is that clear? But if you went to the city, to New York City, that's a very different population than in upper New York State. You do the same thing and you get a very different answer. Okay? So that's the reason we're doing the models in the first place. Is that clear? And that's the difference between what we do and differences and average treatment effects and stuff like that. Okay?
I have a question.
Yeah, shoot.
I have a basic question following up on that. How indispensable is infinite horizon setting of the games for IO application?
I'm going to come back to that. Is that okay?
Yeah.
Okay. That question, by the way, it's an important question. And I'm going to show you that there's a sense in which I can let the future environment be whatever it is. And I'll show you that. Be whatever players think it is, which may be different from the current equilibrium. Is that clear? So okay, and I'll show you exactly how to do that. Okay? I thought you were going to ask a question. No? Okay.
There isn't in the W star, there isn't an object in there that's about the precision of the valuations we have in the States, right?
Right. So I'm going to...
In principle, we could have arrived at an equilibrium where we're quite imprecise, but we just have happened to bounce on
Yes.
Or we could be in a place where we've done this for a ton of time and we're super precise.
Right.
There isn't any statement in that equilibrium up there that takes note of that distinction.
Right. Okay? Okay. So, I mean, it's an equilibrium object. That's it, you know. It's not nothing but how we got there, how precise. It's just an equilibrium object. Okay. Okay, so, you know, this is an equilibrium. Agents could use the learning theory to get there, okay, that I just showed you. The thing that's sort of interesting about this is that, at least formally, it has no cursor dimensionality, this algorithm, because, you know, the recurrent class doesn't necessarily increase with the number of firms or the number of states, okay? There's just, okay, it can stay constant. Usually, by the way, just let me say, the ones I've computed this way, it's linear in the number of firms, okay, or in the number of states. Linear is a hell of a lot better than geometric or exponential, but you can still get in trouble. I mean, it's really a lot better, okay? You can do a lot more. And in this Firstman and Pakes paper, we give, I don't know where I put it here, we'll see, a way of testing if you're at equilibrium at each iteration, okay, or each million iterations. You don't do it at each iteration, it's too much work, okay? Okay, there are ways to even make it more computationally easy, and I'm not going to go there. There's something called TD learning in this paper, this book by Sutton and Bartow. What all that does is it approximates the W's, okay, essentially, okay? So I told you this already. R contains interior and boundary points, and the boundary points can generate more multiplicity than usual. Markov perfect Bayesian equilibrium are a special case of this, and almost every equilibrium concept that's been used is a special case of this, which doesn't say good things about this because it's not doing much. So to narrow the set of equilibria, okay, for where you are today, for the policy that you are at today, you should be able to find out stuff from the data what the policies are, okay, as a function of states. But the other ways of doing it is, I think I said this yesterday, but I'm not sure. Initial conditions, like when I've computed equilibrium, even just two-period games, if you put in the initial conditions, you know, you start somewhere and you fix the starting point. Is that clear? That kills a lot of equilibria, sometimes almost all the rest, okay? Because history determines what's possible in the future. Is that clear? So we did banks for a while, you know, branches of banks. So there's a certain amount of branches that are up now, okay? We're going to change the policy. That says that for certain firms, there are certain things that are possible that make sense, and other firms not, and that's determined by history, okay? So, you know, like the one I gave yesterday, you know, I started at the very beginning of the data, okay, the very first quarter in the data, okay? And, you know, the different firms had different amounts of advertising, different amounts of DCT and prices at that time, okay? And that determined a lot about the equilibrium that we could get. Doesn't determine uniqueness, okay? But it does narrow the set of equilibria, okay? And the other thing is, in this other paper, we gave a boundary consistency condition. The boundary consistency condition just says, look, I'm going to test every feasible point, not just the point that I'm doing. And at every feasible point, I have something in memory for what I get for every M. I'm now in the recurrent class. I look at all the points in the recurrent class, okay? At every point in the recurrent class, I have an expectation for every possible policy. Is that clear? I can test, okay? I'm on a boundary point. I take an M, which is not M star, and I go outside, okay? I have a valuation there. Is that clear? And the question is that valuation less than what I get from staying in the recurrent class with doing the optimal thing? And if it is less for every possible feasible state, okay, we call it boundary consistent. Okay? That's a harder computation to check, but it's doable. So the extra condition for boundary consistency is that for every boundary consistent point, for every boundary point. So you have to check for the boundary points. The WM star is greater than my perception of the expected discounted value at that boundary point. Okay, so I didn't put this in here. I probably should have. If you did the test for the fixed point brute force, okay, so what's the test for the fixed point? It's that this is true, okay? So to find out if this is true, I'd have to integrate out over the possible states of my competitors, and is that clear? So what we show in the Pakes article is that instead of doing that, you can simulate paths, just like Pam was saying, and test whether the simulated paths, okay, that the policies underlying the simulated paths are consistent or not. And the way you do that, okay, is you keep track, you simulate these paths, you hit this point many times. Is that clear? You simulate, because it's a recurrent class, you're going to hit this point many times. Okay. You keep in memory both the variance and the mean at that point. Is that clear? And then you get a consistent estimate of the variance. You keep the variance and the mean there, okay? And you take the difference between your estimate that you have in memory that you got and the average of the continuation values, and you square it, okay? And that square is the bias squared plus the variance squared. Is that clear? You have an estimate of the variance, so you can get the bias squared, and you get the bias squared going to zero, you know, whatever your epsilon is. Does that make sense? I should have put it up here. That, right? So let me do it again, okay, once more. I didn't do the math. It is in the paper, okay? It's much easier to do than doing the integrals, okay? Because you just, so the thing about Robinson-Monroe, just think back what's happening in Robinson-Monroe. Instead of summing out everything, is that clear, over many, many states, I'm taking random draws, okay? And I know the average of those random draws converges. Is that clear? It converges no matter how many states I have. Is that clear? That's the power. Okay, I can have many, many states, and maybe 100 draws is enough to get the average. Okay, is that clear? That's what's going on here. That's why Robinson-Monroe is so powerful. Okay? So in the test, what you're going to do is you hold the policies constant. Okay, I have a W, okay, and you hold the policies constant, and you simulate a bunch of sample paths. Is that clear? And then I average the sample paths at each point, and I average the variance, and I get a variance estimate of the sample paths at every point. The difference between the average that I get from the simulation and the actual W, if I square the difference, it's always bias plus variance, bias squared plus variance. Okay, I have an estimate of the variance, I take it out of the difference, and I'm left with bias squared. Is that clear? And the bias squared, you just get it as close to zero as you want. Okay, that's what's happening in the test. Okay, in the boundary consistency test, I also have to worry about this condition. I have to test for this condition, which we also do by simulation. Okay, it's a lot harder. First, you have to find the boundary points. What does it mean, find the boundary points? At every point in the recurrent class, you have to see what would happen at every other m. Is that clear? Okay. So it's a lot more. And then you do the simulation from every other m. Okay. 10:07. So now I'm going to empirical work. You guys, you should ask questions other than Pamela and other than the. You know, I expected questions from the students, not just the professors. Okay? In fact, I was hoping for questions from the students. I guess I'm going a little bit faster than I thought I would. Okay, I'm going to now go, so this is going to go back to yesterday, but I'm going to do it in a little more detail now, okay? So here's my suggestion. So by the way, so this is really new. So there isn't even a paper out on this yet, but there will be hopefully within a little while, because we're almost finished. But so this is where we're at now. Okay. So I want to use the ideas of the experience-based equilibria in empirical work. Okay. So the original papers, and there's some papers after the original paper, they were all based on doing either theory or computation. Is that clear? There was no empirical work. Okay. So the cost of the goal of this One of the goals of this, one of the goals was to understand advertising, okay? But one of the goals was to set this up, okay, in a way that can be used. Okay, so I need a candidate. If I'm going to do this, I need a candidate for the information set. What does that mean? I need a candidate. I'm going to get back to your question now, okay? Okay. I need a candidate for what variables the firm uses to make decisions on advertising or investment or whatever you're doing. I need to know the variables, okay, that each agent uses, okay? So I'm going to start with an empirical model. So it's going to only assume that firms maximize. Is that clear? Given their perception. Not in equilibrium, they're just maximized. If I assume they're maximized, I can tell you what variables they're using, because I can do a regression on stuff. Is that clear? On stuff in my data, and see if the residual is serially correlated. If the residual is serially correlated, it becomes a state variable in my problem. Is that clear? And everything, okay? So that's what the empirical model is supposed to do, okay? It doesn't impose equilibrium conditions. The guy could be off, could be wacko, okay? But that's what he uses. So I'm going to use so the thing that I've found, and by the way, it's sort of interesting. There's a group of people called Anya Noka, she's now at Carnegie, Kevin Williams at Yale, have been doing stuff on airlines. And the interesting thing was their claim, actually I think it's really interesting stuff. So I'm not trying, I've written letters about this stuff. Okay, so it's not, but they regress stuff on stuff and say, look, firms are not doing the optimal thing, they're doing something else, and here's what the something else is. And what always comes out is the profit function. Okay, they're trying to get to max. There's other stuff too, but always the most important thing is the profit function. Okay, and that's the same thing we found yesterday. Okay, the firms are trying to maximize their value. Okay. It's just too hard a computation. There's no computer, and they know it's too hard for them to do, okay? They're trying to approximate what's the best thing to do, okay? The value function is an iterative of the profit function. I'm just iterating it over time with some policy in the middle all the time, okay? And it works out that the profit function is a really good predictor, okay? And so they say that, okay, in their thing, and it's the same as we got yesterday, okay? So it typically includes a function of profits, institutional features, and controls or states of competing firms, okay? Or some summation over the states of competing. And then, so that's, and then you want to make sure that there's a possibility, at least, of a serially correlated unobserved state variable, okay? Because what are you saying? You're saying, look, I have certain things in my data, okay? Among those things, okay, this is what the firm is responding to. But there's stuff the firm knows that isn't in your data, okay? And like all economic variables, they're serially correlated, okay? There's almost no economic variable which isn't serially correlated, which you would think of as state variable, okay? So you allow for serially correlated state variable. So when you estimate the empirical model, you've got to be careful, okay? So there's going to be, it has profits on the right-hand side and this serially correlated state variable. So, there's going to be an endogeneity issue because the serially correlated state variable is one of the variables on the right-hand side for Paul. Is that clear? And it's correlated with profits today because, it depends on omega yesterday, and omega today is a function of omega yesterday. Okay, so you want to worry about the endogeneity for instruments, okay? Or some other way of doing it, like quasi-first differences. And then selection issues arise if people stop or exit, okay? And what is the selection issue? If I knew everything in the state space that the guy responded to, there's no selection issue. I control for it, okay? That's selection on observables. That's what the statistics literature called. So like the propensity score is one of those, okay? But the problem is you have this unobserved state variable, serially correlated unobserved state variables, and the time you exit is going to be when that has a bad draw, conditional on the other x's. Is that clear? Okay. So the guys who stay in had good draws, conditional on the other x's. Okay. And so the expectation of the residual depends on the x's. Is that clear? So a good draw is a different thing when you have a very high x and a different thing when there's a very low x. Okay. And that will bias everything. Okay. And then what I'm going to do is is I'm going to give you that model and then simulate it just from the empirical model. Okay, so this is empirical. There are no restrictions from theory being brought to bear on this problem. Is that clear? There are econometric restrictions on endogeneity and selection, but there are no restrictions from theory on this problem. Okay? Then I'm going to compute an EBE and do a similar thing. So I'm going to compute the EBE. That gives me, I get a set of policies from here because I'm looking at advertising. I guess now I'm looking at advertising against stuff in a serially correlated error. Is that clear? So that's one set of policies. Those are the empirical policies. This is what Pam would get from data. And Pamela would get from data. Okay. Then I'm going to compute the EBE. That's different because here now I'm imposing the equilibrium conditions. Okay, and seeing what happens. Okay. And then in the counterfactuals, again, one of the reasons we're doing the equilibrium is to be able to do counterfactuals. And the counterfactuals, it's out of sample. I can't do the in-sample thing because there was not a world like that. That's the whole issue of doing a counterfactual. I can't read things off the data because there was never any data like that that was subject to that environment. Okay? So there are two options for getting to the empirical base equilibrium. One is the learning algorithm I just showed you. Okay? So let me just say, the learning algorithm, it works, okay? But it takes thousands and thousands of iterations. And my gut reaction is, so let me take a step back for a second. I don't know if you guys know this literature, but there's a literature on algorithmic pricing now. Okay? That started out with these kind of learning algorithms, okay? Firms just can't do this, okay? If you're Amazon, you have 1,000 things to price. First, a million things to price, okay? You can't price all of them. You're going to write an algorithm of some form to do that, okay? If you did a learning algorithm, it would take you years to get to the equilibrium, to get to the best thing. Is that clear? And, no firm is going to let the algorithm run unmonitored for 3 years, okay? It's just not going to do that. It's going to lose too much money in the middle, okay? So that literature started out with these algorithms, and now it's moving away from them because of this problem, okay? Shoot.
It might be a very easy one, but I don't really understand how you go from the model with the equilibrium where they do not act, the perceptions might not be correct, to the, how do you pose the equilibrium?
I'm going to show you that. Okay. That's the next topic. There. It's a good point. Okay, so that is, in a way, a weakness. So let me show you. Okay, you might think that the demand system hasn't. It depends what changed. If something changed, you put it in. Okay, so the profits. At least it's the static profit function. It doesn't. Prices today don't affect things in the future. Okay, which might be a bad assumption in some cases. I can always do that for profits. Okay. And I'm going to give you a computation of how to get the policy function, okay? But that's going to assume certain things about the stochastic processes underlying the unobservables. I don't see the unobservables in the future. So I'm going to have to keep the unobservables fixed at what happened in the past. That is a problem, okay? And I don't know the way around it yet, okay? Again, what we do in IO, and I tell my students this, in class. They get bored of it after a while. I tell them almost every class. We do the best we can given what we know, okay? And if you can tell me how to do the other one, I'd be happy to do it, okay? But right now I don't know how, okay? Okay, so I'm going to give you an algorithm where I can compute it directly, so I'm not going to worry about the learning part, okay? I'm just going to assume that in the counterfactual I'm doing, you're in equilibrium, okay? Actually, in a boundary consistent equilibrium. Okay? So if we killed DTC today, we wouldn't expect to get there right away at least. Okay? But I'm going to give you where you might have gotten if it was a reasonably stationary environment. Okay? Sort of interesting. I'll come back to this at the end. There's something we talked about at dinner last night that sort of helped me on this. Okay? So, given that you know, it's more appropriate for longer run predictions than it is for short term, probably because of this, you know, you don't get to equilibrium immediately stuff. Okay. So we went over this already. The two problems of computing equilibrium, why it's such a mess, is the state space. Okay, so the amount of states that are in that I need to keep track of. Okay, so each firm and all the state each value for each state variable for each firm. Okay, and then the dimension of the integral that I'm going to integrate out over. Okay, because everybody can move to different places and that can get large also. So here's how I'm going to get around it. Okay, I'm not going to compute for all states. Okay, I'm just going to compute for the states that in this equilibrium that this product would be in every time period. Is that clear? So I'm not going to compute off the equilibrium past stuff. I'm just not going to do it. Okay? So instead of, you know, there's 25 drugs in the market, okay? Instead of computing, you know, and maybe there's about 5 or 6 state variables for every firm. So instead of computing equilibrium for 125 variables, okay, where each one takes on 30 states, okay, which is virtually impossible, okay, I'm going to compute for 15 periods, or I think actually it's 37 periods in the data, okay? For 37 periods and 25 drugs, I'm going to compute equilibrium policies. So that's 37 times 25. That's a number like, I don't know, 25 times 25 is what, 625? So 37, maybe it's 1,000 points, okay? You know, if you, and you know, even the simplest model, you'd get into hundreds of thousands or millions of points for computing it. So I'm not going to do that. And I'm not going to compute the integral, and this goes back to what you were asking about, Pamela. What I'm going to do is I have a policy function at this iteration. For this iteration, okay, what I'm going to do is I'm going to simulate sample paths for the whole industry. I'm going to do that 1,000 times or 100 times, and I'm going to average. And that will be my estimate of the expected discounted value of future net cash flows. Okay? So there's 25 products, 100 simulations, there's 2,500 points. Okay? You got to make sure you keep the random draws the same between the iterations or you'll never converge. Is that clear? Okay, it's just like the stochastic continuity condition in econometrics. Okay. So that's what's going to happen. I'll show you how to do it now. The algorithm is iterative. Iterations are indexed by L here and associated with policy functions. So every iteration has a policy function for every person, for every firm, okay? Is that, okay. And that, I'm calling the policy AT because we were doing advertising, okay? And it's going to be a function of the derivative of profits with respect to C, and it should have been the derivative of C with respect to A, and then some other variables, omega t, WT, and why did I do this? And I should have added omega t there. So I apologize. I had a lot to write up before coming here, and I guess I didn't. So this omega t is up here too. Okay. So the W are the observed variables, things in your data, and the omega t is the unobserved variable. Okay. And the unobserved variable follows the Markov process. Okay. This new t is IID. Doesn't need to be IID, but it's got to be independent of the past. So I'm going to start with the estimate of the policy function that I got from the empirical model. Okay, so I'm going to try and see about an equilibrium that's as close, that I'm going to choose, just because I'm starting there, I'm likely to choose an equilibrium that's very close to the empirical model. The empirical model isn't an equilibrium, okay, but I'm going to choose an equilibrium that's close to the empirical model, okay? At each iteration, I'm going to fix the iteration. So I've fixed the policy functions of everybody, okay? I'm going to simulate out sample paths for the industry, cap K of them. And so I index that by pi KL, okay? So I simulate out for every person in the industry. I go one period, everybody does their best thing. Then given what everybody does and given their experience-based equilibrium policies, I get the next period, I do this. I think we did it for 150 periods. Okay, and I'm coming back to your problem because it's an important problem, but I'll tell you what it is when I get there, okay? Because so what are you doing here? Okay, you're simulating out farther than is in the data, okay? And you might worry about perceptions that are, outside of sample period. What are my perceptions when things are very different from where they are now, okay? And then compute the averages. So I've simulated out k sample paths, okay? Compute the averages of those. That's going to be my perception. That's going to be my estimate, those averages. I'm going to take the expected discounted value associated with those averages, okay? And I'm going to assume that that's approximately the expected discounted value for these policies, okay? So I'm going to assume that they are that this is an approximation for this expectation, okay? I'm going to come back, and then I'm going to say, well, look, if this was the approximation for the expected discounted value, if I subtract, and I know omega t, that should have been indexed by k also, okay? Then I can regress it on the state variables of the problem. And I get another estimate of the policy function. Okay? So this is where I'm going to keep the omega process the same. Okay? So this is the problem that you raised, and it's correct. Okay? And then at the end of the iteration, I'm going to see if I'm going to calculate a metric in the difference between the values at WL and the values at the iteration L and the last iteration. And if that's small enough as a percentage, I'm going to stop. If it's not, I'm going to do it again. Is that clear what's going on? Okay, that's a very simple calculation. Typically, by the way, it's taken us 4 or 5 iterations to get to an equilibrium, okay, which is very small. But we're starting with the empirical model, right, which we think is close, okay? We're getting the equivalent close to that. So I'm going to show you what we had yesterday now. I'm back to what we had yesterday. So these are the fit of the empirical model, okay? And this is, remember, if you remember, there's both detailing and DTC. There's a lot more detailing observations than DTC because a lot of the firms don't do direct-to-consumer advertising. Okay, and you can, so the top ones, as I said yesterday, I'm going to condition on the past. Okay, I guess I didn't bring but you saw yesterday the serial correlation coefficients were like 0.9, 0.95 sometimes. Okay, so conditioning on the past, you should do pretty good. Okay, because 0.95 serial correlation in the error is helping you a lot. Okay, and you see, and in fact you do. You get very high R squares. Okay. But that shouldn't matter. But what should matter is once I condition on the path, I should be on average correct. So the 45-degree line, it should be the empirical policies, okay? The empirical policies and the data should be distributed about the 45-degree line. They compare, and they are pretty much. In the bottom part, it's more complicated. What we did for the bottom part is we said, look, these are just the empirical policies. Now, I haven't put on any equilibrium structure. Okay, I take the empirical policies for the beginning period, and I find out where it would be tomorrow from a random draw. Is that clear? And then I do it again. I take the predicted policy tomorrow, and I predict 2 years from now, and so on. I do that 37 periods out. Okay, and this is a fit of one side of this is data, and the other side of this is the empirical model. Yeah. And one is for detailing, one is for DC. As you might expect, this is going to be a lot more variant than the one, okay? Because over 37 periods, your initial omega doesn't help you very much, okay? And it's worse for DTC than for detailing. That's, in a sense, that's good for us because it's the detailing we want to get right if we kill the DTC. So then we go to EBE with estimated primitives. So the EBE now is going to do the computation here. Okay, it's going to get it this way. Okay, this is this algorithm. I'm going to now compute the policies that come out of the fixed point of this algorithm. Okay, and then I'm going to show you what they look like. Okay? Yeah.
Sorry, I don't mean to take away some time from the students, but what determines the functional form of this policy?
It was an assumption that I made early on.
I know, but why
did a lot of stuff with the data, and this came out as what people did. I mean, we use linear, we use cross products also and stuff like that, polynomials. But the answer was the thing that mattered the most was the derivative of the profit function. The other 2 or 3 things that mattered were what the firms competing in the same ATC class, so the same type of molecule, SSRIs or statins, okay, were doing. They're advertising, okay? And the third thing that came out all the time was the time to loss of exclusivity when the patent goes out. Because when the patent goes out, you stop advertising, okay? And you stop it slowly as you approach it.
But why do you take the law of the derivative?
Because that's the way you get out so you take the log, okay, and because you're going to take the derivative with respect to xi, which in the BLP, okay, and xi we modeled, seeing it's an exponent, we modeled it as a function of log advertising.
Oh, I see.
Okay? So it's just sort of like, it's a Cobb-Douglas function, essentially, okay? It is a Cobb-Douglas function, actually. We didn't start there, but that's where we ended up. That's what fit the data, okay? You got to speak louder. You have to give her a microphone. Sorry. I don't know if this is a function of age or not.
So I think I'm still a bit confused about not computing all the policies for the possible states. But so it's like you choose one product and then compute the path of that product, keeping other products fixed. But your profit function will still have the other. So if you're like one company but produces different products, those products' profit function, because of like spillover effects across products, should be embedded in that profit function, I would assume.
Okay,
But
so
you're keeping that fixed and compute a path.
So I'm not really doing that. So let me come back, okay? So I start out with this policy function. Is that clear? That fixes theta. That fixes a set of parameters. Fixes beta W. It fixes these thetas. Is that clear? They're fixed, okay?
Oh, so pi is not a profit function of the firm.
Pi
it's
is
just
the
a
profit
pay.
function.
Oh, okay, yeah.
Okay?
Uh-huh.
Okay. It might depend on parameters too. I just didn't put it in there. It doesn't matter, okay? I go through this iteration, okay? And at the end of the iteration, whoops, I do this regression. Okay? That gives me the new parameters. Gives me a new beta, okay, and a new theta, and it would give me a new profit function also. Okay? I then substitute that in for the next iteration, and I keep on going until I hit a fixed point.
Oh, I see. Okay, yeah. I think
Okay.
that makes sense. Yeah. Thanks.
So if I get the idea right, we do not really care what's off equilibrium path, so we do not really care about the values there.
I'm not saying I don't care. I'm saying I'm not computing.
Yeah. Well, this is kind of the same. So this gets you rid of the computational burden. But what if? I mean, this is fine if you are staying in equilibrium path. What I do not understand currently is what happens if you do the counterfactual analysis and you get off the equilibrium path. How do you deal with the?
Okay.
Yeah.
So what's going to happen in the counterfactual analysis? I'm going to compute this again. Well, I'm going to shut down DTC. Okay, I'm just going to compute another equilibrium or I would change the profit function, or I would change whatever I'm going to change, and I would just recompute this thing. That's what we did. So the computation, I'll give you a second in a second, okay? So the computation, what you're doing in the counterfactual is you're changing something in the structure of the institutions of this market. You plug those new institutions in and you recompute the equilibrium for the new institutions. Okay, now you can ask more if you want. Are you okay with this?
Yeah, I think this needs to sink in a bit, but yeah, thank you.
I think we need to defer some of the questions for
Okay.
because
Okay.
we're 12 minutes into the break.
Oh, we are? Okay. Anyway, so let me just, so we did this, and this is a comparison. It'll be 1 minute. This is a comparison of the empirical model to the experience-based equilibria. And you can see it's not exactly the same. Okay, so, the data says, and the same thing for detailing. The data says that, we weren't exactly at the equilibrium I was computing, okay? The interesting thing is here, and I'll stop, this is my last slide. So this is, the blue is the empirical model, and these are the fit over the 37 periods in sample, okay? And the dashed line is the theory model. What's sort of interesting is that the empirical model fits better initially, okay? But worse followingly. So you can interpret this in different ways. We were talking about this last night at dinner, okay? One way to interpret it is, they weren't quite at equilibrium, okay, in the empirical data, but eventually, they were moving towards it, and we eventually got closer to it. So eventually, the theory works better than the empirical work, okay? Or you can interpret it that we're overfitting on the empirical model, so it's not estimated as well as, and the structure that we're putting on is correct, okay? So you can interpret it either way. I don't know the real answer. It's sort of interesting. Thank you. I'm happy to talk to people who want to. I'll stick around for a bit.